We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard.
Godspeed, John Glenn.
Roger, 0G, and I feel fine.
I feel the liftoff. The clock has started. Roger.
This is a new and strange environment at first. Just suddenly finding yourself in orbit.
We have a liftoff, 32 minutes past the hour. Liftoff on Apollo 11. Houston, Tranquility Base here. The Eagle has landed.
Hello and welcome. This is Michael Annis, and you're listening to episode 43 of the Space Rocket History Podcast. And now, Ranger-7, Nimbus-1, European Space Organizations, and Christmas from the Moon. During 1964, there were several significant unmanned scientific missions launched. Two of them will be covered in this episode. The first is Ranger-7. As part of the pre-Apollo preparations, NASA created the Ranger series of missions to take high-quality pictures of the Moon and transmit them back to Earth in real time. These images were not only to help select landing sites for future Apollo missions, they were also used for scientific study. Some spacecraft of the Ranger series carried gamma-ray collection equipment as well as equipment to study radar reflectivity of the lunar surface. The plan was to dive straight into the Moon while sending close-range pictures back to Earth during a period of about 10 minutes prior to impacting the lunar surface. You may recall from episode 32, Ranger-4 was the first U.S. spacecraft to reach another celestial body. However, it failed its primary mission of returning pictures from the Moon. The next attempt was Ranger-5, but 15 minutes after launch, a malfunction led to the transfer of power from solar to battery. Battery power was thus depleted after 8 hours, and all the spacecraft systems died. The first mid-course correction was never implemented because there was no power, and Ranger-5 passed by the Moon at a range of 724 kilometers instead of impacting the Moon. And of course, there were no close-up pictures sent. The next attempt was Ranger-6. Ranger-6 was successfully injected on a lunar trajectory. The mid-course trajectory correction was accomplished successfully, and on February 2, 1964, 65 hours after launch, Ranger-6 impacted the Moon on the eastern edge of the Sea of Tranquility. But still, there were no pictures sent. The camera system had failed. A review board determined the most likely cause of failure was due to an arc-over in the TV power system when it inadvertently turned on for 67 seconds, approximately 2 minutes after launch during the period of booster engine separation. And now, Ranger-7. The Ranger-7 spacecraft consisted of a hexagonal aluminum frame base 1.5 meters across, on which was mounted the propulsion and the power units, topped by a truncated conical tower which held the TV cameras. 2 solar panel wings, each 74 centimeters wide by 154 centimeters long, extended from the opposite edges of the base with a full span of 4.6 meters. And a pointable high-gain dish antenna was hinge-mounted at one of the corners of the base away from the solar panels. A cylindrical quasi-omnidirectional antenna was seated on top of the conical tower. The overall height of the spacecraft was 3.6 meters. I posted a picture of this on the homepage. The launch vehicle was an Atlas 250D and an Agena B6009, similar to the previous Ranger launch vehicles. Propulsion for the mid-course trajectory correction was provided by a 224 Newton thrust monopropellant hydrazine engine with 4 jet vane vector control. Orientation and attitude control was enabled by 12 nitrogen gas jets coupled to a system of 3 gyros, 4 primary sun sensors, 2 secondary sun sensors, and an earth sensor. Power was supplied by 9,792 solar cells contained in the 2 solar panels, giving a total array area of 2.3 square meters and producing 200 watts. 2 1200 watt-hour batteries rated at 26.5 volts with a capacity for 9 hours of operation provided power to each of the separate communications and TV camera chains. 2 1,000 watt-hour batteries stored power for spacecraft operations. Communications were through the quasi-omnidirectional low-gain antenna and the parabolic high-gain antenna. The spacecraft carried 6 television cameras. 2 of them were full scan cameras, 1 for wide angle and 1 for narrow angle, and the other 4 were partial scan cameras, 2 wide angle and 2 narrow angle. The cameras were arranged in 2 separate chains or channels, each self-contained with separate power supplies, timers, and transmitters so as to afford the greatest reliability and probability of obtaining high-quality video pictures. Unlike its predecessors, no other experiments were carried on Ranger-7. Of course, the mission of Ranger-7 was the same as the previous Rangers, to achieve a lunar impact trajectory and to transmit high-resolution photographs of the lunar surface during the final minutes of flight up to impact. On July 28, 1964, Ranger-7 was successfully launched from Cape Canaveral Launch Complex No. 12. The Atlas 250D and the Agena 6009 boosters performed nominally at launch, inserting the Agena and the Ranger-7 into a 192 altitude Earth parking orbit. Half an hour later after launch, the second burn of the Agena engine injected the spacecraft into a lunar intercept trajectory. After separation from the Agena, the solar panels were deployed, attitude control activated, and spacecraft transmissions switched from the Omni antenna to the high-gain antenna. The next day, July 29th, the planned mid-course maneuver was successfully accomplished at 10:27 Universal Time. Ranger-7 reached the Moon on July 31st. The cameras began their 1-minute warm-up 18 minutes before impact. The first image was taken at 13:08 Universal Time at an altitude of 2,110 kilometers. Transmission of 4,308 photographs of excellent quality occurred over the final 17 minutes of flight. The final image taken before impact had a resolution of 0.5 meters. After 68.6 hours of flight, Ranger-7 impacted in an area between the Sea of Clouds and the Ocean of Storms. This is the general area where Apollo 16 would land. Impact occurred at 13:25 Universal Time at a velocity of 9,432 kilometers per hour. The spacecraft performance was excellent, and Ranger-7 became the first spacecraft to send close-up pictures of the Moon. I posted a NASA video on the homepage that shows Ranger-7's final movements before impact. Here is a couple excerpts from the video.
During the 17 minutes that Ranger's full-scan cameras operated, the A camera recorded 200 pictures of the lunar surface. More than 4,300 pictures were taken by the 6-camera system. The TV pictures from Ranger-7's cameras were received and recorded at the Goldstone Tracking Station in California's Mojave Desert. 1.5 minutes to impact. Small craters, possibly made by debris splashed from the major craters Copernicus or Tycho, come into view. 48 seconds to impact. 33.4 miles from impact. An area 4 miles on a side is shown. 3.5 miles to impact. Impact, July 31st, 1964.
Ranger-7 is also credited for beginning the peanut tradition at NASA command stations. On the success of Ranger-7, someone in the control room was noticed eating peanuts. Surely, the reason the mission was finally successful. Since 1964, control rooms ceremonially open a container of peanuts for luck and tradition. Now let's move along to Nimbus-1. Nimbus-1 was the first in a series of second-generation meteorological research and development satellites. It was designed to serve as a stabilized Earth-oriented platform for testing of advanced meteorological sensor systems and for collecting meteorological data. The spacecraft was designed in two sections. The lower circular ring housed the meteorological sensors and electronics. The upper hexagonal section contained the altitude control system, and it had two solar panels with 10,500 individual cells attached to its sides. The two sections were constructed by a magnesium truss. The lower ring was 145 centimeters in diameter. The total spacecraft height was 3 meters. The width across the solar panels was 3.4 meters. The total weight of the spacecraft was 376 kilograms. It sort of resembled an ocean buoy. Nimbus-1 carried three types of cameras. First, an advanced Vidicon camera system for recording and storing remote cloud cover pictures. Second, an automatic picture transmission camera for providing real-time cloud cover pictures. And third, a high-resolution infrared radiometer to complement the daytime TV coverage and to measure nighttime radioactive temperatures of cloud tops and surface terrain. On August 28, 1964, Nimbus-1 was launched from Vandenberg Air Force Base in California and inserted into a polar orbit. The launch vehicle was a Thor Agena B. Unfortunately, a premature cutoff of the Agena second stage left the craft in an elliptical orbit rather than a more circular one. To make matters worse, one of the solar panels failed 26 days into the mission. In spite of these problems, 27,000 pictures were taken and 60 ground stations were involved in the direct readout of this imagery. The infrared imagery was much clearer than those sampled by the Tyros series of satellites, and Nimbus-1 became the first satellite to provide images of complete world cloud cover on a daily basis. 1964 was also an important year for European space research. Two organizations were founded that year. First, I want to cover the European Space Research Organization, or ESRO. It was created as an initiative of European scientists to pool government resources in support of space science. The ESRO convention entered into force on March 20th, 1964. The 10 founding states were Belgium, Denmark, France, West Germany, Italy, the Netherlands, Spain, Sweden, Switzerland, and the United Kingdom. Two other countries, Austria and Norway, decided not to join the new organization, but retained an observer status. The first meeting of the Council opened in Paris 3 days later on March 23, 1964, with Harry Massey in the chair. Pierre Auger was appointed ESRO's first Director General. The convention outlined that the organization would be solely devoted to space science. During this operation, the ESRO launched about 300 sounding rockets, with 168 dedicated to ionospheric and auroral studies. About 25% of the sounding rockets were used for atmospheric physics, and the rest for solar, stellar, and gamma ray studies. The organization also launched 11 small satellites 4 space probes, and 2 large satellites. The other organization I want to talk about is the European Launcher Development Organization, or ELDO. It began as a multinational consortium formed in the 1960s with headquarters in Paris. The purpose was to build an indigenous European space launch vehicle. ELDO came about after the cancellation of the Blue Streak program by the British government in April of 1960. Since the development of this missile was almost complete, it was planned to use it as the first stage of a satellite launcher. Britain then proposed a collaboration with other European countries to build a 3-stage launcher capable of placing a 1-ton payload into low Earth orbit. ELDO began work in 1962 and was formally signed into existence in 1964, bringing together Germany, France, Belgium, Italy, the Netherlands, and Britain, with Australia as an associate member. Britain was to provide the first stage of the launcher, France the second, and Germany the third stage. Experimental satellites would be developed in Italy and Belgium. Telemetry and remote controls in the Netherlands, and launches would take place from Woomera in Australia. Overall, there were 10 launches that occurred under ELDO funding. In 1974, after an unsuccessful satellite launch, the program was merged with the European Space Research Organization to form the European Space Agency. Thanks for listening to this archive episode of the Space Rocket History Podcast. If you are financially able, please support the podcast by going to the homepage, spacerockethistory.com, and clicking on the orange Donate button or the Patreon link. Thanks.